All right, so you can hear me?
Yes, sir.
Okay, great. So is there any question from anyone from the last lecture?
No, sir.
Okay, I'll just quickly remind, we saw vectors. How do we add vectors? At first, we looked at a complicated case where the vectors may not be parallel to each other, and we saw how can we find the resultant vector, right? And we derived this expression for this one, which was FR squared. F is equal to the sum squared of all the forces. And we saw how will we find the direction of that force respective to some horizontal line or something, right? And then we saw a very simple case, which is of adding parallel vectors. And that's very simple because you just sum all the vectors to get a resultant vectors. It's also sometimes called the principle of superposition of vectors. And so you can, that's why, add these vectors like this. And then we started about talking about forces and how does a force contribute to motion, where we moved our discussion to Newton's laws of motion, and we talked about the uh, first law of motion given by Newton, which is simply that the first law of motion simply states that every object will really continue to be in a state of motion or a state of rest unless you act on it by some resultant or net force, right? And so that I can give you, I think I can talk at this point about something that is also called balanced forces, which would really come under the idea of first law of motion, right? So let me make this a bit larger. All right. Okay. So suppose that I have, again, I always give this example, but bear with me. Suppose there is a table, and the table, it's a normal practical table that you would encounter in your daily life. There's nothing special about it. There is a book on this table, and now suppose that the book is stationary, sitting still on the table, right? Would you expect it to move if you don't do anything to it? No, right? The book will not move. But suppose that I apply
No,
some force in this. Yeah, so suppose that I apply some force in the right direction, and let's just say that's the vector F, capital F vector. Um, what would you expect would happen now?
the book will move to the right.
The book will move to the right. Uh, as soon as the book starts
And the book will move
moving,
forward.
yeah, exactly, right? So but as soon as the book starts moving forward, would it experience anything else, maybe another force or anything? What would will there be some other
Friction.
force? Yeah, can you repeat?
It will face friction.
It will encounter friction, right? Exactly, and that's due to the contact of the book with the surface of the table. So as soon as the book starts moving, a new force develops, which is the frictional force between the book and the surface of the table. I'll denote it with small f, and it will oppose the direction of motion which was produced by the capital F, right? This one. All right, now the book has started moving, but now suppose that the force that I applied becomes equal, or you can say that the friction that is developed, it becomes equal to this force that I applied. What would happen at that point?
The
Would you expect the
the,
book to stop? The
the
book,
book will not move, sir.
okay. Okay, so yeah, that's the
stop.
misunderstanding that I thought that it might be. Okay, so yeah, the book will not stop, right? It will not stop. Um, you might think that the book will stop because there is no force on the book, right? And the reason you would think that is because you're associating force with motion, and we do that normally. Anyone would think like that force is completely associated to motion or velocity. It kind of is, but you have to remember that force is proportional to the acceleration. Really, we know that force is equal to ma. I'm sure that we haven't gotten to this thing F equals ma as of yet, but I'm sure you are all aware of this expression. Is there anyone who has never seen F equals ma in the class right now? Anyone?
No, sir. So I think everyone
Everyone
has
has.
an idea what might happen, sir. So
Yeah, so you have seen the expression F equals ma, and we have already discussed that we have discussed in effects of forces over here, that when you apply force, it would cause a push or cause something to move or accelerate and so on, right? We discussed that. So then the idea that force produces acceleration is well and good, but you have to remember that it is not directly talking about velocity. It is talking about change in velocity, right? So as soon as I remove the force, or you can say that the friction and capital F becomes equal, acceleration would be zero, net acceleration would become zero, right? But and what that means, that velocity will not change, right? So that would mean that delta v, change in velocity, would become zero when this happens, which means there is no change in velocity, but it would still be moving because velocity itself is not zero, right? But now you can of course argue that because of the other air resistance and everything, uh, and more or less because of the air resistance, the book will eventually come to a stop, right? But suppose that you were doing this in the vacuum, then the book would not stop. It would keep moving with the constant velocity. It would just stop accelerating. So is that idea clear?
Yes.
Yes.
yes, sir.
Okay, great. All right, so that's an example that I wanted to give. When this happens, this is known as a balanced force, right? Or balanced forces. These two forces together, when they become equal, then the forces on this system or the object are balanced, and hence balanced forces would not produce any net acceleration, right? Okay, so that's great. Now we can move on to before we talk about Newton's second law, we can talk about something else also, which is known as, now I'll start with the name, unbalanced forces. Now, what would you expect to be an unbalanced force? If I consider again this example of the book on a table, right? Suppose I'm
One
considering.
force is, I think one force is like friction is more than force. The friction is more than force, or the force is more than friction.
Yeah, exactly, right? So, for example, if the forward force, the push is capital F, so the friction is small f, then an unbalanced force is very straightforward, that when F and small f are not equal, right? So when they're not equal, then that's the case of an unbalanced force. And what would that do? That would produce a net acceleration, right?
Sir,
So, for example, if F is great, yeah, are you asking something?
can you repeat
If
it
you have a
again?
question, please.
Wait,
I cannot hear you.
sir.
Can you
And
please?
it also produce deceleration.
Yeah. So I'm coming to that.
Can you repeat unbalanced force?
I'm
Can
asking,
yeah, you're
sir,
saying, can I repeat?
there is a
Okay, let me just repeat the unbalanced forces, right? You're there are two questions at this point. I think one is that if I can repeat the unbalanced forces, right?
Yes.
I don't know, either it's my internet problem or I cannot hear you. Can you speak a bit loud? Hello. Okay, so I cannot hear any. Okay, wait. There is
hello,
something
sir.
in
Can you
chat.
hear?
Teacher, he said,
Unbalanced.
can you
Got it.
repeat
Got it. Got it.
unbalanced forces?
Yeah, got it. So if I say that, if I'm saying that I cannot hear you or something, so yeah, that's a good idea. You can always type in chat. So I always have this chat open with me. I'll read your chats from there, right? Okay, so yeah, unbalanced forces. Suppose I have a book again on a table, the same example, but now in this case, I apply a push to the book. So the book will start moving forward, obviously. But now suppose that the friction that develops, it is not equal to that force of push, right? Suppose that it does not, for some time, it does not become equal to the forward force, capital F. If that's not equal, then of course, when I do this thing, F minus F, it will not be zero, right? In case of an unbalanced force, because these two are not equal, and hence it will not be zero, but it would be some other number. So I'll just call it, let's just give it this hash name. It's a number. So there would be some number, and that means that there would be a net acceleration on the book. Now, coming to the next point where I talk about would it be acceleration or deceleration, that thing completely depends on this thing, that if F minus F is greater than 0, or if F minus F less than 0. Now, can you tell me in which case of these two would I experience acceleration, and in which case would I experience deceleration? Anyone from the class? Make a
So,
guess. Any prediction?
in the in the first case, we will experience acceleration, and in the second, you'll expect deceleration.
Exactly, right? So, and can you also tell the reason to the entire class as well? Why would that be? Why is that case?
When the first in the first case, the force is greater than the friction, so
Yeah.
the object will be able to uh, mm, the body will be able to get an acceleration.
Yeah, because the forward force, which is acceleration, which is causing the book to move in the direction that I want it to move, right? That force is overcoming friction. So that's why acceleration. Yes, you got it exactly right, right? And in the other case, we experience deceleration because now friction is more, and friction always opposes the direction of motion, and hence that would produce a deceleration or a negative change in velocity, right? So the velocity would be decreasing. So, all right. So that's clear for everyone.
Yes.
Could you explain that again?
These 2 points.
Yes.
Yeah, sure. Okay, so imagine that you're pushing a book that's just sitting still on a table, right? Now, when you push this book, you're applying some force. Now, you're applying the force to push the book forward, right? That's your intention. That's what you want to do. You want to make the book move forward. So when you want the book to move forward, you say that you are accelerating the book, right? The book is gaining some speed and it's moving forward. All right. So if the force that you apply overcomes the frictional force, produced by the contact of book and the surface of the table, then you'll have to excuse the noise. I hope that's I think it's bothering you. I'm not at my home right now, and is there any noise? Can you hear any noise? Dogs barking?
Yes, sir, it's fine. It's really small.
Okay. Sorry for that. I apologize for that. Yeah. So coming back to this thing. So yeah, I'm applying a force to move it forward. If I want it to move forward, I'll say it's accelerating. So if the force that I'm applying, which is capital F, to move the book forward, if that's greater, then I would be accelerating the object, right? The object would keep gaining speed. But if the frictional force, which is the force that is opposing, that wants to stop this motion, if that force becomes greater than capital F, then the object starts slowing down, right? And hence, that means deceleration. Is that clear, Purva?
Yes.
Okay, great. So this thing is clear for everyone now?
Yes.
Yes, sir.
Okay, great. Amazing. All right, so if that's clear, then we'll move to Newton's second law of motion. Let's just write it like this, second law. Okay, so anyone has any idea what is Newton's second law before like I get into it? Does anyone want to volunteer?
So is it
Okay.
force equals to mass times acceleration?
Yeah, so the mathematical expression for that is you got it right. It's F equals ma, right? It's F equals ma. Okay, so but the statement or the concept or what does F equals ma means is also very simple. It just means that a result. So I don't know if I should write the statement entirely, but anyways, I'll write it. So whenever you have a resultant force, which means that there is net force acting on the system. So the sum of all the forces is not zero. If that's the case, then this resultant force, which is acting on a body, will produce, what would it produce?
Accelerate.
Change. Yeah, exactly. Or change in velocity or acceleration, right? Change in velocity, which is known as acceleration, right? So it would produce an acceleration or change in velocity. Another thing that you can say is it would cause a change in momentum. Are you familiar with momentum? Okay, it doesn't matter. Even if someone is not familiar with momentum, we'll not talk in terms of momentum, but it produces a change in velocity, right? So that acceleration that it produces in the system, it would depend on the direction of the resultant force. The direction of that acceleration or change in velocity would depend on the direction of this resultant force. So I can write this expression as F equals, or you'll say that, of course, if we talk in terms of proportionality, we always make our equations by seeing on what factors does my quantity depends on. So the force depends on, or you can say acceleration depends on the force. So the larger the force that I apply, the more acceleration I'll produce. And that's kind of obvious if you think about your daily life, right? So you experience this all the time. So we can then write this thing as F equals m times a. Now, this statement is still not complete. One way to kind of move towards the completion of the statement is by adding a summation sign next to this force, right? What that means is that the sum of all the forces will produce an acceleration, right? So there should be some net force, right? If the net force is 0, then there will be no acceleration. So this thing just means that if I have F1 plus F2 plus F3 and so on, this would altogether combine to produce a net acceleration on this mass m. So what can you conclude by this statement and this expression? What does it tell you? What is happening? Well, first thing is obviously clear that a resultant force, so I'll just say Fr, will do what? It will produce acceleration. So that's something that we got from the statement as well. So it will produce acceleration. Anything else that you can conclude from, or if you look at the equation, for example, suppose that I triple the acceleration, what would you expect the force to be? So meaning, suppose I say that the acceleration is 3 times a, what would that do to force?
Force will increase as well.
Triple, sir.
Force would increase as well. Or actually, I should have started from this thing that if I say the force is increased 3 times, that would produce a 3 times acceleration, right? You could go the other way around as well, right? So if something is accelerating 3 times, then it usually should be, then that means the force was tripled. All right. So now another interesting thing is that suppose that I say that the force does not change. So I have applied a force and it's constant, right? So F is constant. I do not change F. I don't want to change F. What would happen if I double the mass of my system? So force is constant, mass is doubled. So mass becomes 2 times m. What would happen to acceleration?
It will decrease.
Anyone?
Acceleration will decrease.
Yeah, but can you give me a figure by how much?
By 2 times, I think.
Yeah, so it would become half of its initial value, right? So it would be 1 by 2a. All right, good. So everybody understands this?
Yes.
Is it clear?
Yeah.
Oh, okay. All right, good. That's good. That's good. Okay, so all right. You learn Newton's second law in this language in terms of acceleration, really, I think in O levels. But a better version of Newton's second law is in terms of momentum, but I don't think that's that's in your syllabus. So we'll skip that and talk in terms of F equals ma. Actually, you get F equals ma from that the original statement of Newton, where he talked about momentum. Really, he defined a quantity called momentum, and then he defined force in terms of momentum. That's what Newton's original work, right? And then we can conclude from that that it's equals to m times a. And yeah, so is Newton's the idea of Newton's second law clear to everyone?
Yes.
Okay, great. So now you're going to help me do a problem, a very simple problem, just to see if you understand Newton's second law. Suppose that I'm standing here and I have a box in front of me, and suppose I apply a force, or you can say I'm pushing this box away from me. So let's say I'm applying some force to do that. Suppose that this box is heavy. It weighs 20 kilograms, right? Sorry, its mass is 20 kilograms. And suppose that I can calculate the force that I'm applying to this box. Suppose I know that this force is take 50 newtons, right? Take it to be 50 newtons. Now, can you tell me what would be the, how fast would be the change in velocity, or can you tell me what would be the change in velocity of this object, or in other words, what would be its acceleration? How, can anyone tell me how would can I conclude from these quantities what would be the acceleration of this box?
Yes, you can by changing the formula you can no, by rearranging the formula you can.
Yeah, so F equals mass times acceleration, and well, I know my force and I know the mass of this object, and I'm looking for how fast would it start to change its velocity. So I'll just say that acceleration is force over mass, and you'd put the values and you'd do it, right? So it was very simple. Clear for everyone?
Yes, sir.
Yes,
And now, okay, so in what direction would this acceleration be?
right.
To the right. And you say that because
Because the force is on the right.
on the
Going
right,
to the
exactly,
right.
right? Yeah, so good, very good. Okay, so you have to so the point here was also to always remember that the acceleration vector will always point in the direction of the force vector, right? So the acceleration vector would be parallel to the direction of the force vector. All right. Okay, so I guess let's now we can move on to Newton's third law. Newton's, I'm sure you're all familiar with it, right? Can anyone tell me what is Newton's third law? I mean, I believe that you'd all be familiar with it. People make lots of jokes with Newton's third law. They say that if I slap you, you would slap me back with the same force.
Every
Yeah,
every action has an equally opposite reaction.
yeah, exactly, right? So that's as simple as it is. Every action done, or you can just say every action has an equal but opposite reaction. Opposite, ignore my spellings, reaction. Now, is everyone familiar with this statement?
Yes.
Yes.
Right? Okay. So if you're familiar with this statement, can you tell me, for example, I'm standing on a ground, right? It's a ground, it's the surface of the earth. I'm standing on it and I want to walk, right? Suppose that I want to walk. Why can I walk if every action has an equal and opposite reaction? So suppose that I apply a force backwards to move forward, right? But I mean, because because of this thing that every action, so this action would have an equal but opposite reaction. So I mean, normally you would expect
The ground will, the opposite reaction is on the ground. How can I explain this in words?
right. So I got your point, and I understand now that you know the reason for that. But so some people, you might, it's very normal for someone to look at Newton's third law, and then they will have questions that, for example, this is an example of a ground and a person, right? I'll give you another example that might be more clear. Suppose this is a swimming pool, and there is a swimmer in this swimming pool. So ignore my drawing, right? Completely ignore my drawing. And of course, the swimmer, he's going to push against the water, and then you would expect him to move forward, right? Now, if every action and reaction are equal but opposite, so that means that if this is some F, then this should be some minus F, right? So sign is different, but the force, the number of force, for example, if it was 10 newtons, so I'll give it a number. If this was 10 newtons, then this is minus 10 newtons, right? So then he should not be able to, swim really, but he's still able to do that. So anyone else, can you tell me? I think Taha and Muiz, they know the answer. Anyone else?
So maybe
Yeah,
his
just think
force
about
is
it.
not I don't know, sir. So I always heard of this law, but I never really understood it, sir.
Yeah, so I mean, it's very normal to have this confusion that, in your daily life, you'd think that this law is being violated at every moment in life, right? You'd think that, well, this does not make sense. How am I able to walk? How am I able to do anything really, for that matter? But you have to, the key point of this thing is to remember that the forces act in pairs in such a way that these would be acting on different bodies. They're not acting on a same body. So if they're acting on different bodies, I would take, for example, the resultant force. If I take this person, the resultant force on this person would not be 0, because the other force would be on the ground. So I cannot say that if I'm taking this person as my system, I cannot say that I will just do F and minus F, which would become 0. That's not the case. You take a system, and for person, if the system is your person who you want to see, will he be able to walk or not, then the system is the person. And the net force on this person is not 0, because the other force is acting on the ground. So there are two systems over here, and the other system is the ground. And on the ground, the net force is minus, right? And that's the reason that you're able to move. So there is some net force on you. Similarly, if you look at the case of the swimmer, the force is acting in pair, right? They are equal in magnitudes, right? But they are opposite in directions. But the key point is they're acting on two different bodies. The swimmer pushes against the water, applies the force on the water, and the water applies equal and opposite force on the swimmer. So there are two different bodies in play. So if I take my swimmer, who I want to see, will he move forward or not, then I'll take the system as a swimmer, and I'll see that on the swimmer, there is net force, right? And that net force is in this direction, which came into being because the water applied an equal but opposite force in this direction, right? So minus F, you can say, if that was F. So the key point is that these forces act on two different bodies. Now that was, I'm sure that most of people, they have this confusion. At this point, after this explanation, is it clear for everyone?
Yes, clear
Or,
for me.
Yeah.
okay, so it's clear. If for everyone it's clear, you'll never have this confusion again, right?
So can you
Now
explain
you
it again,
understand.
sir?
I don't get it for some reason.
Okay, so you want me to explain it again? That's what you're saying? Sorry, I did not hear.
Yes, sir.
Okay, so I'll do it over here. God damn this dog. Anyways, okay, so all right, let me just draw this thing again. So we have a swimming pool, water, and there's a person inside this pool who wants to swim, right? Now what he does is according to Newton's law, if this person pushes against the water with his legs, Newton's third law says that the water would push this person as well in the opposite direction. So if this is F applied by the person, so I'm calling it FP, then water applies an equal in magnitude force, but in the opposite direction. So it would be applying a force in this direction, which would be the force that is applied by water.
Yes, sir.
Now,
I get it now.
yeah. So now the thing is that the confusion for everyone is usually that if these two forces are like this, if Fp is equal to you can say if these are both equal in magnitudes, then it's equal to F minus Fp, right? In the opposite direction, because the magnitude is same. The better way to not confuse you is give these forces numbers. So if this is 10 newtons, then F water is minus 10 newtons, right? That means that the forces are equal and opposite in direction, right? Now, yeah,
Teacher, you can
yes,
explain
yes.
it in terms of chair, a chair. Like someone sits on the chair is you put force on the chair when you sit, and the chair puts opposite force on you, so you can sit.
Yeah, you can, of course, you can explain it in terms of that as well. But I guess if I explain it using a chair, then I might not be able to get this point across, because on a chair, yes, you're sitting,